Hello everyone, welcome to the 21st lecture of the course Discrete-time Markov chains and Poisson processes. So, in the last lecture we saw that if Xn is an irreducible positive recurrent Markov chain, then starting from any state I, the long run proportion of time the chain visits state I, or the long run proportion of time the chain spends in state I, that is equal to pi I, which is the unique stationary distribution, where pi I is equal to 1 over Ei Ti, right. So, we saw that stationary distribution appears as a limit, right. That showed that stationary distribution is indeed important, because I said that it is a very important thing. We have already seen many important properties of stationary distribution. In today's lecture, we will see some more. And another thing that we saw in previous lecture was this complete characterization of states in terms of this PIIK, like when it is transient, recurrent, positive recurrent and null recurrent. So, if sum over k running from 0 to infinity, PIIK is less than infinity, then it is transient. If this quantity is equal to infinity, then it is recurrent. Now, in order to further subclassify it into positive recurrent and null recurrent, we need to look at this quantity, which is 1 over n plus 1 sum over k running from 0 to n PIIK. If the limit of this is equal to 0, then it is null recurrent, and if it is positive, then it will be positive recurrent. Fine. Okay. So, today we will see some more limiting theorems. So, the first theorem, that this long run proportion is pi I, that was one of the limiting theorems. Fine. So, this module is about limiting theorems. So, today we will see one more very important limiting theorem. So, let us start. So, we saw that if it is positive or null recurrent, so we saw this kind of a thing, right, that 1 over n plus 1 k running from 0 to n PIIK. So, say if I is, so this converges to 0 if I is null recurrent, and this converges to 1 over Ei Ti if it is positive recurrent. Fine. So, again you see that we already saw that this long run proportion is equal to the stationary distribution, but again what is this Ei Ti? Now, since it is positive recurrent, suppose we are assuming irreducibility as well, then this is precisely the stationary distribution. So, we see even the limit of this thing 1 over n plus 1 k running from 0 to n PIIK, that is equal to the stationary distribution, the ith component of the stationary distribution, if the state or if the chain is irreducible and positive recurrent. Now, for a state I, what about this limit? Because remember what is this? So, it is starting from I, Xn equal to I. Does this have a limit? So, as n goes to infinity, does this converge to something? Remember, if you recall, one of the theorems that we saw in the module of stationary distributions, we saw that if you have a finite state Markov chain, then this Pijn, the limit of that, if it exists, we called it as limiting distribution, and if it exists, that has to be the stationary distribution. So, basically this, you start from a state and then probability that you add Xn equal to j as n goes to infinity, does this converge to something? That theorem said that if this limit exists, then that has to be equal to the stationary distribution, but it didn't say anything about when or whether the limit exists or not. So, here we are now trying to investigate that part, whether that limit exists or not, but here we are, instead of I and j, we are just looking at I equal to j. Again we will see finally when we see the result, we will see everything for I j, but initially first let us concentrate on PIIN. So, whether this starting from I probability xn will be equal to I if this as n goes to infinity if this limit exists. In order to answer that question, first let us look at an example. So, we consider the Markov chain with the following transition probability matrix. So, the Markov chain has two states 0 and 1, and the Markov chain is actually very simple. So, if this is 0, this is 1, it just goes from 0 to 1 with probability 1 and it goes from 1 to 0 with probability 1. So, it is an extremely simple Markov chain, and it is easy to see that it is irreducible because you can go from any state to any state, and if you just try to calculate you will see that this has a unique stationary distribution given by half comma half. So, you can easily check that. Now, as soon as it has a unique stationary distribution or just because it has a stationary distribution it is irreducible. So, all states are positive recurrent. So, it is a irreducible positive recurrent Markov chain with these stationary distributions. So, in that sense it is a nice Markov chain. Now, let us see for such a Markov chain if whether this limit exists or not. Now, here you see since like it is a very the dynamics of the Markov chain is very simple, it goes from 0 to 1, 1 to 0, right. So, starting from 0 the probability that it will be at 0 in odd number of steps, that is 0 because it goes from 0 to 1, 1 to 0. So, it is at 0 at all even steps. So, P002n minus 1 is equal to 0 and P002n is equal to 1 for all n greater than or equal to 1. Now, that is very simple from the dynamics of this Markov chain, but that tells you that this limit does not exist because what is this? Like if you look at, so this if you look at this, so this P00n is nothing but just a real sequence. So, and how does that sequence look like? So, it is like in or so P00 is so if I just look at from say the first, so odd place you have 0 and even place you have 1. So, it is a sequence of 0 and 1s. So, obviously, this does not have a limit, right, because the lim sup of this is 1 and lim inf of this is 0. So, you know like this kind of an so it is kind of an alternating sequence. So, the limit does not exist. So, you see for such a simple Markov chain which has all these properties of irreducibility, positive recurrence, unique stationary distribution, still this limiting distribution does not exist, fine. But now the question is, okay, then is there some issue with this Markov chain? Now, in order to understand that, first we need to learn a definition, the definition of a period. Now, what is period of a state? So, period of a state I is defined by the greatest common divisor of all integers n greater than or equal to 1 for which this PIIN is strictly greater than or equal to 0, i.e. what is DI? DI is the GCD of all n greater than or equal to 1 such that PIIN is strictly greater than 0 if this is a non-empty set. If this is an empty set, then we define the GCD to be equal to 0, define the period to be equal to 0, fine. Now, what is greatest common divisor? Again, this is something you should know from high school. So, given a set of numbers, what is the greatest common divisor or the highest common factor? That it is also called the highest common factor. So, what is that? It is basically, so great again, so it is greatest common divisor. So, the name itself will tell you what it is. So, first of all it has to be a common divisor. So, if you are given a set of numbers, so in this case the set of numbers is the set of all n for which this PIIN is strictly greater than 0. So, I look at this set of numbers. Now, the greatest common divisor is a number which is first of all a common divisor. That means, it should divide each number in that set. It is a common divisor and it is the greatest common divisor. That means, if you have any other common divisor, that will be less than or equal to that, right. Say for example, if I look at if my set is 4 and 8, right. So, if my set is, so here it is, suppose my set is 4 and 8, then 1 is a common divisor because 1 divides everything, 2 is a common divisor, 4 is a common divisor. But what is the greatest common divisor? 4 is the greatest common divisor, fine. But in this case, this set can be an infinite set. Fine. So, actually, so when this is non-empty, this actually will be an infinite set. Fine. So, but again it does not matter, it is the same thing. So, the greatest common divisor of a given set of numbers, finite or infinite does not matter, is a number, is that number which is a divisor of all the numbers in that set. So, it is a common divisor, and if there is any other common divisor, that has to be less than or equal to this GCD. It is the greatest common divisor, also this is called the highest common factor. Fine. So, what is this period? The period is the greatest common divisor of this set of numbers. What are the numbers? So, it is the collection of all those n greater than or equal to 1, for which PIIN is strictly greater than 0. That means, starting from I, you can be at I in the nth step with positive probability. Fine. If n is such that for which this probability is positive, then you take that n. So, when you look at the collection of all such n's, that gives you a set of numbers. The greatest common divisor of that set of numbers is called the period of that particular state I. Fine. And if this set is empty, then you call it then you just define the period to be 0. Fine. The important case is this first case when it is non-empty, right. Further, if I is called aperiodic if the period is 1. Fine. Okay. Now, let us see some examples to understand this concept of period better. So, again consider the Markov chain. So, this is basically the example which we saw in the previous. So, example 34 and example 35 is the same Markov chain. In 34 we saw that this Markov chain does not have the limiting distribution, or in other words limit n going to infinity PIIN does not exist. Now, let us see that what is the period of say 0. Now, we have already seen that P002n minus 1 is 0 and P002n is equal to 1. So, now what is this set? The set of all n greater than or equal to 1, where PIIN is strictly greater than 0. So, this is precisely the set 2, 4, 6, which is the set of all even numbers. Now, what is the greatest common divisor? So, 2 because is a common divisor. So, basically 1 and 2 are common divisors of set of all even numbers, because if you take anything greater than 2, that will not divide 2. So, 1 and 2 are the common divisors of the set of all even numbers. Among them 2 is the greatest. So, D0 is equal to 2. Similarly, see, for even 1 also this same thing is true, that P112n minus 1 is equal to 0 and P112n is equal to 1, because the 1 also you go to from 1 to 0 and then you come back to 1. So, starting from 1 you are at 1 at even steps. So, even by the same argument you can also check that D1 is also equal to 2, right. So, here we see that this one thing is there, that here it has period 2. So, is that a problem? Because of which this PIIN, the limit of that did not exist. Okay. It can be, because we saw why it did not exist, because if we looked at this sequence of PIIN, it was this alternating 0 1 0 1. So, maybe there is some connection with this periodicity thing. Fine. Okay. But that we will see slightly later. But before that, let us see one more example. So, now we look at this S. So, the state space is the set of all integers. So, 0 plus minus 1 plus minus 2 and so on. And suppose you starting from I. So, again you go to from I to I minus 1 with probability A. You go to I from so this is I plus 1 and say this is I minus 1. So, you go from I to I minus 1 with probability B and you remain at I with probability C, where A plus B plus C equal to 1, where A is strictly greater than 0, B is strictly greater than 0, C is greater than or equal to 0. Now, fix a state I. Now, suppose that PII1, so again what is PII1? That is just simply PII. PII1 is PII, right. So, that if from here that is equal to C. So, if that is strictly greater than 0, that means if I look at this set, the set of all n greater than or equal to 1, PIIN strictly greater than 0. So, then 1 belongs to that set, right. So, 1 belongs to the set of all n for which PIIN is strictly greater than 0, because PII1, which is nothing but just PII, that is C, which is strictly greater than 0. So, if C is strictly greater than 0, 1 belongs to this set. Now, as soon as 1 belongs to this set, the only possible common divisor is 1, because if you take anything greater than 1, it will not divide 1. Remember, common divisor means it has to divide every number in that set, and as 1 is in the set, anything greater than 1 cannot be a divisor. So, 1 is the only common divisor, and hence it is the greatest common divisor. So, in this case, the di is equal to 1. Fine. So, or in other words, if C is greater than 0, then I is what is called aperiodic. So, in this case, I is aperiodic. Okay. Now, that is if C is strictly greater than 0. If C is equal to 0, that means what? You can go from I to I minus 1 and I to I plus 1. So, again, so this is just simply like a simple random walk, right. And in a simple random walk, we saw that if you are starting from a state, you can come back to that state only in even number of steps. You cannot come back to that state in odd number of steps, right. So, again, for any I, this is equal to 0, and now this is positive. Again, not like the previous example, it is not 1, but it is strictly greater than 0. So, starting from state I, there is a positive probability that you come back to I in any even number of steps. For example, if you have to come back in 2 steps, say there are 2 ways of doing that. Either you go from I to I plus 1 and then come back, or you go from I to I minus 1 and then come back. Fine. So, all these for any even step, this probability is strictly greater than 0. So, now if I look at again this set of all n greater than or equal to 1, where PIIN is strictly greater than 0, that is again the set of all even positive even integers. So, 2m, m greater than or equal to 1. Now, we have already seen this in the previous example. The only common divisors are 1 and 2. So, 2 has to be the greatest common divisor. So, in this case, di is equal to 2. So, depending on whether C is strictly greater than 0 or C is equal to 0, we get 2 kinds of things. So, if C is strictly greater than 0, then the period is 1, and if C is equal to 0, then period is 2. Fine. And now again you see, so here you see I have done it for any state I. So, it is true for all states. Now, even in this previous example also you saw that the period is same for both the states. Now, is there something special? Yes, like transience, recurrence, positive recurrence, null recurrence, even period is a class property. So, if I communicates with j, then di is equal to dj. In both the previous examples that we saw, it is very easy to check that both the Markov chains are irreducible. So, every state has the same period. In the first example, it was both 0 and 1 had period 2. In the second example, if C is strictly greater than 0, then all states have period 1, and if C is equal to 0, then all states have period 2. So, even period is a class property. So, if I communicates with j, then di, the period of I is equal to period of j, right. So, a small thing, let me just, so here, so basically, so instead of this we should write it as di equal to dj, that is the notation that we are using, not d bracket I, but d subscript I, fine. So, if I is equal to j, if I and j communicate, then di is equal to dj. So, if I and j is in the same communicating class, then they have the same period. So, states in the same communicating class have the same period, or in other words, periodicity, just like recurrence, transience, positive recurrence, null recurrence, is again a class property. Fine. So, if Xn is irreducible, then all states have the same period. In particular, if all states have period 1, we say that the Markov chain is aperiodic. Just like if all states are recurrent, we say the Markov chain is recurrent, or if all states are transient, we say that the Markov chain is transient. Similarly, if it is an irreducible Markov chain and all states have period 1, then obviously all states will have the same period. Now, if it is equal to 1, then we say that the Markov chain is aperiodic, right? Okay. Now comes the important theorem, which says that let Xn be an irreducible, positive recurrent and aperiodic Markov chain. Then for any initial distribution mu, so that means what is mu? So, mu is like probability x0 equal to I is mu of I, that is the meaning of any initial distribution mu. Then limit n going to infinity p mu, again p subscript mu means just this, that you are starting from the initial distribution mu, Xn equal to I, this exists and is equal to pi I for all I, where this pi I belonging to S is the unique stationary distribution. Again, since it is irreducible and positive recurrent, we know that the stationary distribution exists and it is equal to the it exists and it is unique and it is equal to 1 over EI Ti. So, again this quantity or the limiting distribution is the stationary, the unique stationary distribution. Now, see, this is not, again we have already seen this, at least for in the case of finite state Markov chains, that if the limiting distribution exists, then it has to be stationary distribution. We have already seen this result. The question was when the limiting distribution exists. So, here we give a condition on the Markov chain under which the limiting distribution exists. So, namely if it is irreducible, positive recurrent and aperiodic, then for any initial distribution mu, so no matter what initial distribution you start with, this limiting distribution, by limiting distribution I mean this quantity, that starting from any initial distribution, the probability that at the nth step you will be in state I, as n goes to infinity, that converges to pi I, where pi I is 1 over EI Ti, because this is a irreducible positive recurrent Markov chain. So, it has a unique stationary distribution pi, where pi I is EI Ti. Fine. So, in particular, suppose my mu is delta I. So, that means if I say start from I, and then if I look at say starting from I, what is the probability that Xn equal to j? This, as n goes to infinity, will converge to pi j, right. So, here I am looking at the special case where my initial distribution is delta I, or I start with from I with probability 1. Fine. So, since this is true for any initial distribution, I can obviously choose my mu to be delta I. So, for any two states I j, limit n going to infinity, p I j n equal to pi j. So, in the theorem in the module of stationary distributions, we saw that for if it is a finite state Markov chain, then if the limiting distribution exists, that has to be stationary distribution. But what this theorem is telling you is giving you a condition or a set of conditions rather under which this limiting distribution exists. So, that this is equal to pi j is actually not surprising, that this is equal to the stationary distribution is not surprising, but the important thing is this what. So, the main content or crux of this theorem is condition under which the limiting distribution exists. So, the first example which we saw, namely this example. So, what was the issue with this? The issue with this example was that it had period 2, right, because we have seen this here that this Markov chain has period 2. So, this is not aperiodic, hence that is why. So, for the limiting distribution to exist, this aperiodicity is needed. If it is not aperiodic, the limiting distribution may not exist. Fine. So, if the Markov chain is irreducible, positive recurrent plus aperiodic, then the limiting distribution exists and it is equal to the stationary distribution. So, you see again like why stationary distribution is important. So, what this basically tells you is that it says that, so you start from any, so we have seen that if you start from a stationary distribution, you remain there. That means all the distribution of each xn is equal to that stationary distribution, fine. But now if you start from any initial distribution, what this theorem is telling you is that as n goes to infinity, probability xn equal to I, that is equal to pi I. So, even if you do not start from the initial distribution, if your chain is irreducible, positive recurrent and aperiodic, then basically the chain moves towards the stationary distribution. So, that is why some books also use the term equilibrium distribution for stationary distribution, because every system wants to go towards the equilibrium. So, if the chain is irreducible, positive recurrent plus aperiodic, then the no matter what initial distribution you start with, the chain will eventually move towards the stationary distribution. That is not a very precise mathematical statement. The precise mathematical statement is this, that limit n going to infinity, p mu of xn I is equal to pi I. That means the limiting distribution is the stationary distribution, fine. And this theorem is telling you something more. So, that remember when that theorem in the module for stationary distributions, the theorem was only for the statement of the theorem was only for finite state Markov chain. It said that if it is a finite state Markov chain, then if the limiting distribution exists, then it has to be stationary distribution. But what this theorem is telling, okay, you do not need actually finite state Markov chain if the limiting distribution exists, and the limiting distribution again even if it is a infinite state Markov chain, and provided it is irreducible, positive recurrent and aperiodic, then the limiting distribution exists and it is equal to the stationary distribution. So, even if you do not start from the initial stationary distribution, you eventually move towards the stationary distribution. So, that is why it is also sometimes called an equilibrium distribution. So, that is because every system wants to move towards equilibrium, and if you have an irreducible positive recurrent aperiodic Markov chain, then its distribution moves towards the stationary distribution, fine. Now, I will end with one just small remark that this kind of a Markov chain, if it is irreducible, positive recurrent and aperiodic, some books also use the term for such a Markov chain, they use the term ergodic. So, if in a book you see that xn, let xn be an ergodic Markov chain, that means it is irreducible, positive recurrent and aperiodic. So, ergodic is a common term used for if a Markov chain has all these three properties, that it is irreducible, positive recurrent and aperiodic, then such a Markov chain is also called aperiodic. So, I just wanted to mention this because in some book you might encounter the book on Markov chains, discrete-time Markov chains, you might encounter this terminology ergodic, and this is what it means: irreducible, positive recurrent and aperiodic, fine. So, what we have seen today is two more important properties of stationary distribution, again not two more, actually like one more, that it is actually the limiting distribution. So, we already knew it for the case of stationary for the case of finite state Markov chains, but there we did not know when the limiting distribution actually exists. So, today we saw a criteria under which the limiting distribution exists, and also, so once the limiting distribution exists, it is equal to the unique stationary distribution provided the chain is irreducible, positive recurrent and aperiodic. So, you see, so suppose someone asks you, okay, if you look at a chain of, so long time from now, So that is the meaning of, so in real life, what is the meaning of limit n going to infinity? Suppose the chain starts from now, at the current time, and someone asks you, so if you now look at the chain a long time from now, what is the probability that you will, that the chain will be in state I, right? Then the answer is, if the chain is irreducible, positive recurrent and aperiodic, then in the long run, the probability that you will find the chain in state I is equal to pi I. That's the way you should interpret this mathematical theorem, that, or the mathematical result, that the limiting distribution is pi I. So in the long run, if you look at the chain, the probability that you will find the chain in state I is equal to pi I, where pi I is the unique stationary distribution. So we also know what this pi I is. It is nothing but 1 over EI TI. Fine? Okay. So we will stop here today. Thank you all.